Hello everybody, and welcome back to our third and last lesson about confidence intervals. And so the first two lessons we've talked about confidence intervals for a population mean. Now we're doing something a little bit different where we're talking about population proportion. Okay, so we're talking about percentages here. It wouldn't be correct to call it a mean. It's a proportion. We're interested in what percentage of a population does something or believes in something or is something. Okay, and this is really goes back to the idea of binomial experiments in a way, because you're in this and the way in this game that we're playing, we're taking a random sample. And we're asking them a yes or no question, yes, do you do blank or do you believe in blank? Okay, it's either a yes or no. And we define a success as just if they say yes. And so, but things are a little bit different now because with binomial experiments, the value of P and Q were known ahead of time. In this case, we're trying to get an estimate to find what that is. All right, and what we're doing is we're getting an estimate by using we're taking a point estimate, but in this case, our point estimate will be a fraction. Okay, so when we say let P be a population proportion, that's what we're talking about. P represents a percentage of a population that does blank or believes in blank or supports blank. Okay, and P is always a number between 0 and 1. And then we take a random sample, size n, from that population, and we let x be the number of, well, we could say the number of people, but it could just be the number of items in the sample that do blank, whatever we define a success to be, right? So x is going to be some number between 0 and n, and then we define p hat as x divided by n. That's the percentage of people in our sample that do blank, okay? And make a success. And then we'll see that we'll also need this complementary estimate, Q hat, which is just 1 minus P hat. Now, the reason why this works, we need Q hat is this. As long as n times P hat and n times Q hat are both at least 5, then we can go ahead and find a confidence interval for this proportion. And we say that P is going to be between P hat minus E sub C and P hat plus E sub C, where E sub C is this number right here. I should say C represents our confidence in the level of confidence in our interval, or in our estimate. And in this case, E sub C is defined this way, where it's this number, this critical value is E sub C times the square root of P hat times Q hat divided by n. Where Z hat is the same as it was in section 6.1. It's the Z hat Z sub C is the right boundary of this region for this middle region under the standard normal curve, where the area of this is C. Okay, so again, for our purposes, the Z sub C is either going to be one of those three values, 1.645 or 1.96 or 2.575, okay, most of the time. But that's how we get that. And that's how we define, this will be our margin of error in this case. Now, in the other side of this coin is, let's say we don't know what our, before we take our sample, let's say we already know what we want the margin of error to be. Well, then we do this. We say that if the minimum sample size needed for E sub C to be less than or equal to E, okay, so if we want it to be within, let's say we're given E and we want E to be our margin of error, then we need N to be equal or preferably greater than this number here, P hat times Q hat times Z sub C over E quantity squared. Now, this is the minimum sample size we need. Now that's great, except we have this p hat and q hat are results of a sample. So how can we use p hat and q hat, where the only way we can get p hat and q hat is if we take a sample? Okay, kind of silly. So the way we do that, you handle that, is if you've done this before, if you've gotten estimates, an estimate in previous years, let's say, we can use those for p hat and q hat. Or if you have no idea, if you don't have any preliminary estimates or previous estimates, you just use p hat. I let p hat and q hat be 0.5. Okay, and that will work as well. So this is how these are the two formulas that we need for this section. And I do want to show you why does this all work? Why do these formulas work? So if we look at page 2, we'll see why this works. Why do these formulas work? Well, now, and I say this won't be on the test. So if you're not interested in seeing why this works, you can feel free to close this video and go on to the next part of the next video. Okay. But why do these work? Well, recall that we know that we can approximate a binomial random variable using a normal distribution in certain situations. That is, if NP and NQ are at least 5, where in this case, N is the number of trials, P is the probability of one success in a trial, and Q is 1 minus P. So X is approximately normal. That is, it's approximated by a normal distribution with mean NP and standard deviation, the square root of NPQ. Okay, this was all done in chapter 4 and chapter 5. Now, p hat, we can view p hat as a random variable just because we have x divided by some constant n. Okay, so this will also, because x is approximately normal, then n is also approximately normal with the mean. In this case, we take the mean of x divided by n. Well, that's just p. And we take the standard deviation of x divided by n, and we can do a little algebra with square roots, and some n's cancel, and we get this pq, square root of pq over n. So that's where this comes from. And then in this case, we're saying that this, since this is p hat is normal, it's approximately normal with this mean and this standard deviation. Well, that would mean that this random variable has it's approximately the standard normal distribution, because you want to think of this as kind of like the z-score of p hat. Okay, so this is p hat minus p over the square root of pq over n. So now we see that C then, because C represented that area under the normal curve, standard normal curve, C represents a probability that this expression is between these two critical values, minus C sub C and Z sub C. And then we can multiply both sides by the square root of PQ over N and do a little more algebra or inequality stuff. We can multiply both sides by -1, and as we described last time, that doesn't change much. It just interchanges these two. And then we can add p hat to both sides, and we get p hat minus this number is less than p, which is less than p hat plus this number. And this number, now the only difference is that we can't just plug in p and q, because we don't know what p and q are, right? That's what we're trying to estimate. So we use our estimate, p hat and q hat. We use p hat as an estimate for p and q hat as an estimate for q. And this works. So that's where the formula for the margin of error comes in. For the minimum sample size, we have, this is just a little more algebra. If we want the margin of error to equal E, that means that this expression is equal to E. we divide both sides by z sub c, then square both sides, then take the reciprocal of both sides, and then finally multiply by p hat and q hat, and we get this. Okay, so it's just a little algebra. Okay, and one thing is, most of the time this is not going to be a nice integer, so we take the next integer bigger than whatever this number is. Okay. All right, so that's the proof of this. The proof of this will not be on the test, but what will be on the test is the examples in the next video. So I'll see you then.